So the homework 2, the deadline for homework 2 is February 3rd, I guess, of February 1st. So I guess it's the next Tuesday. So you can start it to work on homework 2 from now on. Yes, it's next Tuesday. Yeah. And for homework 1, do you have any questions? We can briefly talk about homework 1. Any questions? Yes.
Problem 1 says compute the real and imaginary parts. 2, come up with ECE equals sign that. Yeah. Okay. 2, so how to approach that?
This one?
Yes.
Okay.
I have to make that with you, but I don't think so.
Okay, let's see. Compute the real and imaginary parts of the complex numbers. So this is a product of 2 complex numbers. This one is in the polar form, right? It's exponential, and the other is in the Cartesian form. So to get the real and the imaginary parts, they are defined in the Cartesian form. So the idea is to simplify or rewrite this quantity into the standard Cartesian form. And we have a Cartesian form here. So what we need to do is to somehow translate this polar form into a Cartesian form. And there's a formula that translates complex exponentials into Cartesian form, the Euler's formula, right? So you just apply that. So EJT is cosine t plus j sine t. So this is that exponential part, and then multiplied by the whatever inside. Yeah, and then you just do a calculation. And yeah, when you do j square, it is -1. So you need to be a little bit careful here. Okay, so other questions? Problem 1 is compute complex number. Problem 2 is calculate the energy. Problem 3 is calculating the power. I have one question here for this one, for this signal. How do you calculate so in order to calculate the power, you need to first identify the magnitude, right? It is in that formula. So how do you calculate the magnitude of xt for this example? This one? Yeah. So how do you get the magnitude of this one? And this is an addition of 2 complex numbers in their polar form. Is there an easy? I mean, there are definitely multiple ways to do that, but is there a convenient way to get the answer? You can first apply Euler's formula and then translate everything into a standard Cartesian form. So you end up with a standard complex number in the Cartesian form. And then you can calculate the magnitude based on the square root formula. But that will involve a lot of sine cosines. So computation there's a little bit involved. So is there an easier way to do that? Well, if we define this to be a complex number z, right, this is a complex number. Then the magnitude of z is, in the class we mentioned this formula, z conjugate. Oh, sorry, the magnitude square. Therefore, you just need to calculate the square root of this one. So that is the magnitude. And this makes seems pretty easy because, well, we can try to work this out. So z is, because now you are multiplying the conjugate with the complex number z. And for multiplication, we know that polar forms works very well for multiplications. So this is the z part, the first part, and its conjugate. The conjugate of the entire thing is the addition of the conjugate of each individual part. So the first part taking conjugate. Now this is the polar form. So taking conjugate, we just need to revert the sign of the phase part. So this becomes negative j omega t. And the second part becomes positive. So you do this, and then you just do a calculation, and you can see that if you multiply these two, this exponential part will cancel out. So that makes the calculation pretty simple. So you get a1 square. And then you do this two, you get a1, a2, j2 omega t. And this one is a1, a2, e negative j2 omega t. And finally, the last one is a2 squared. Okay, and you can keep simplifying. Let's keep put everything together. A1 squared plus a2 squared. Now that is these two parts, and these two we have a common factor a1 a2. So inside we have j2 omega t plus e negative j2 omega t. And then this one can be further simplified. Remember that whenever you see a pair of complex exponentials and they are conjugated with each other, you can always recall the inverse Euler's formula. So I believe this gives you ej theta plus e negative j theta. That is 2 times cosine theta. So it's a1, a2, 2 times cosine 2 omega t. Okay. So we end up with this simplified formula. Can we go one step further here? I guess this is probably the simplest we have. Yeah, okay. So I think that is it. Yeah, so this is the magnitude of z of this signal. And then you plug in this one into the power formula. In the power formula, you need to take a square of this magnitude so you can get rid of this square root. So basically that integration is integrating over whatever inside. And it is pretty simple because the first part is a constant. So that part, the integration is pretty simple. And the second part is that it's basically a cosine omega t, it's a cosine function. So integrating cosine function, again, should be simple. Okay. So this is how you work out the magnitude for this signal. This is a superposition of two complex exponential signals. Okay. And we have this, the last one is scaling and shifting of the signal. For the first one, well, we can look at one of them. Let's just look at second one. So if we want to do shifting first, yeah, to 1, right? Because we have this t plus 1 here, so we can first go to, oh, if you do 1, let's see, okay, so let's write out, this is equal to x1 half t plus 1 half. I think if you do shifting first, you need to shift to the left by 1 half. Okay, let's try both approaches and see what is the difference. So this is shift to the left by 1 half. And then in order to introduce this scaling factor to the t, so this shift to the left by 1 half. And then I just need to further introduce this scaling factor to the t. And this is a standard time scaling. So this is kind of like expanding the time axis by a factor of 2. So then I do this 1 half t. Scale. So the time scaling by the factor 1 half. Now, if you do shifting by 1 first, okay, maybe this is your motivation, right? If you do that first and then do the scaling, what you get is after you scale the t variable, that one still remains. Okay, so this is yeah, this will be different. Yeah, if you do shifting first, you need to use this formula, this version. Yeah, so if you want to do shifting first, you need to identify the overall shift of this function. It is 1 half. So this one is not, okay. Now, what about the other way? We can do scaling first. If we do scaling first, we can look at this one. Well, we can see that t is scaled by 1 half. So we can first do a scaling. This is a standard scaling. It's expanding the axis by a factor of 2. And then we need to introduce this shifting factor. From this expression, we can see that we just need to replace t here by t plus 1. So that is a shift to the left by 1 unit. We just need to replace the entire t by t plus 1. But and here from the first approach, if we after we introduce the shifting, if we want to do a scaling, you can see that all we need to do is to replace the entire t by t over 2. So that's why this is a standard scaling operation, scaling by 1 half. Okay. So this is homework 1. And then you can sketch the signal after you do the scaling and shifting. And homework 2 is about, yeah, today we will talk about homework 2, the lecture 2, basically. Let's look at last time we talked about periods, operations of the signals, shifting, time scaling, and their combinations. And we mentioned these periodic signals. This concept should be very intuitive. And we have these even and odd signals. So by definition, every signal can be decomposed into an even part plus an odd part. So today we will go over a bunch of very useful signals that we will see in the entire course. Okay, we have sinusoidal signals and their complex exponential versions. And then the last two are very, very useful. We have unit step functions and the impulse functions, especially the last one, the impulse function. Okay, so let's go over them one by one. Now, sinusoidal signals is very simple. Xt, the standard form is xt equals to cosine omega t plus theta. And well, this t is the time variable, and we call this omega the angular frequency or the radian frequency. Theta is called the phase component of this signal. And sometimes we write this angular frequency as 2 pi times the frequency f. So in that sense, the signal can be also rewritten in this way, where we replace omega by 2 pi f. So here, this omega and this f, they have different units. F, the unit for f is the hertz. And the unit for omega is the rad per second. So they have different units. And we can see that this signal, it can be obtained from cosine t by standard operations. For example, we can do time shifting first, right? Time shifting first, and then do a time scaling. So it's shifting by theta and then scale the time axis by the factor 1 over omega. Okay. Now the period of this signal is 2 pi divided by omega. This is because cosine t has a period, 2 pi. Right? This is the period for standard cosine signal. And time shifting does not change the period because it doesn't change the scaling of the signal. So after a time shifting, the period is still 2 pi, right? And then after time scaling, the period will become different. So we know that the scaling factor is 1 over omega. So this is 2 pi. Now the period 2 pi will be scaled by the scaling factor 1 over omega. So it's 2 pi divided by omega. I add an absolute value in case it is negative. So this is how you calculate the period of this signal. And then we have this complex sinusoidal signal. It's basically it's a complex signal whose real and the imaginary parts are both sinusoidal signals. So it's A cosine omega t plus theta. This is the real part. This is a standard sinusoidal signal plus J times another sinusoidal signal. But this here we have sine. And then by the Euler's formula, this can be written in a very compact way. It's A times EJ omega t plus theta. So we can see that for this complex sinusoidal signal, the amplitude or the magnitude is a constant A. Now, as t varies, the phase component of this signal will change. So it is omega t plus initial phase theta. Okay, so this is the complex sinusoidal signal. It's basically a generalization to the complex domain. And we have these exponential signals. It's basically e to the power of a parameter sigma times t. And depending on the sign of this sigma, it could be exponentially decaying if sigma is negative, or exponentially increasing if the sigma is positive. And this should be very clear from these two figures. And then we can have this, we can combine the exponential signal with the sinusoidal signal to generate this damped or growing sinusoidal signals. So it's basically, we have a standard cosine signal, cosine omega t plus theta. And then we scale the amplitude by the exponential signal, e to the power of sigma t. So you can see that depending on the sign of this sigma, the signal, this cosine signal may be exponentially damping. The amplitude may be exponentially damped or exponentially increasing depending on the sign of the theta, of the sigma. And then we can further generalize the exponential part to a complex version. Well, for this complex exponential signal, its real part, both of the real part and the imaginary part are the previous exponentially scaled sinusoidal signals. Okay. So both of the real and the imaginary part takes this standard form. Okay. So here the imaginary part has a sine instead of cosine. And then you can apply the Euler's formula to write them in a single exponential form. Okay, so these are very standard signals, and they should be very clear from the context. So once I give you the signal, you don't have to remember the name, and you can always refer to the slides. But once I give you this signal, you can understand mathematically either it is a real signal or a complex signal, and what is the real part, what is the imaginary part. And the next function is a very special and very useful function called the unit step function. It is an idealized signal. Defined, the shape looks like a unit step. That's why we call it unit step function. So it is defined as if t is less than 0, then the signal is basically 0. And starting from 0, the signal takes a constant value 1. So we have one step. We take one step starting from 0. So we end up with this unit step function. And by definition, it is a causal signal because the signal only exists as when t is greater than or equal to 0. Now that's the definition of causal signal. And it is not continuous, right? There's a jump at 0. So when t is less than 0, we have 0 amplitude. And once we reach 0, the amplitude jumps to 1 instantly. So at this point, this signal is discontinuous. And this unit step function is very useful because it can be used to create causal signals, right? If you multiply any signal, if you multiply any signal by this unit step function, and then this is definitely causal. Because by the property of UT, this UT will only preserve the signal xt when t is greater than or equal to 0. Okay. For all the negative t's, UT is 0, so you have 0 signals when t is less than 0. So this makes every signal causal by multiplying it by UT.
Can you repeat that?
Sorry, you need to repeat this.
Yeah, can you repeat how it creates a causal signal? I don't quite
Yeah.
see it.
So the definition of causal signal is that the signal can only take non-zero values when t is greater than or equal to 0. That means this signal, in order to be causal, the signal must be 0 when t is less than 0. Now the question is, how do we make, for example, this signal is not causal because there are some there exists some non-vanishing signals in the negative part. So the way to make this a causal signal is by multiplying this signal by the UT function. And you can see UT in the negative part, UT is always 0. So therefore, this 0 signal multiplied by this negative part will always give us a 0 signal. So it will zero out the negative part of this xt. So after multiplication, we only end up with, you can draw this figure here.
That makes sense. Thank you.
Yeah. So after multiplication, we only preserve the positive part. Okay, so this is so mathematically we can play this trick, or we can say that given any signal xt, if we want to consider the causal component of this signal, then we mathematically we just write down xt times ut. That will automatically give you the causal part of the signal. And also the unit step function can be used to extract part of another signal. We will see one example right in the next slide. But as you can see in the first item, by multiplying any signal with ut, we are basically extracting only the signal in the positive domain. And moreover, later in the following slides, we will see these units, many other special signals can be created by the unit step signal. Okay, so let's see some further applications of this signal. The other very special signal is called unit rectangle signal, which can be created by the previous unit step function. So let's look at this signal. This is the illustration of the signal. The definition is that between is a unit rectangle, so it looks like a rectangle. So between negative half to half, the signal takes a constant value 1. Otherwise, it is all 0. So you can see that this is exactly a rectangle shape. The width is 1, and the height is also 1. So, and it is centered at 0. So this is we call this unit rectangle signal. And very interestingly, this rectangle signal, mathematically, it can be written as in this form. Let's check this out. Is the unit step function. Take one unit step function, shift it to the left by 1/2. Right? This is by the standard time shifting operation. We are here we are plus a positive number, so the signal is shifted to the left by 1/2. And then we are minus another unit step signal that is shifted to the right by 1/2. We can actually verify this. Now, there are two ways you can verify this, either visually by drawing a picture, by visualize these two unit step functions, and then by doing a subtraction by looking at the pictures, or you can do this mathematically. Okay? But drawing a picture is always intuitive at first. So let's look at this one. The unit step function is here's 0. Looks like this. And the first signal is shifting the function to the left by 1/2. So we will generate this unit step function. Right, and similarly, the other one is shifting to the right by 1/2. Okay, and now we can verify. So remember here we are doing subtraction. This signal in the top will minus the signal in the bottom. So clearly this is a segmented signal. So we will divide this into several cases. If t is less than 1, the negative 1/2. If t is less than this point, both signals are 0. So 0 minus 0 will get 0, right? That's what we have here, 0. And between negative 1/2 to 1/2, between these 2 points, we can see that this signal is 1, as constant value 1. And in between the second signal, the second unit step signal has a constant value 0. So 1 minus 0, we get 1. So that's why we get this constant 1 between negative 1/2 and 1/2. And then beyond this 1/2, both signals take value 1. So 1 minus 1, we get 0. Again, we get this 0. So this is how we create this rectangle signal by subtracting 2 shifted unit step functions. Okay. And the unit step signal can also be used to define this unit ramp function. Now this ramp function is defined as, again, if t is less than 0, there's nothing there. Now starting from 0, we have a linear, the signal is linearly growing. So RT equals to t when t is greater than or equal to 0. So this is a linear function in time. And turns out that this signal can be defined in terms of the unit step function in this way. It is basically the integration of the unit step function from 0 up to the time t, And this is very intuitive because if you consider the unit step function, and imagine you are integrating this function starting from 0 to another point t. So as this t moves to the right, the integration is basically the area under this constant curve. And this area grows linearly as t increases. So by integrating this unit step function, the integration will have a linear increase in time. So that's why we get this formula. So it's basically integrating the unit step function starting from 0 up to a time t. Right? Because when s, this integration variable s is greater than 0, when s is greater than or equal to 0, unit step function takes value 1. So this is equals to 1 ds, which is t. That gives you this ramp signal t. So this is the ramp signal. And on the other hand, because it has this relation in terms of this integration, on the other hand, we can say that ut is the derivative of this ramp function. Right? By taking the derivative on both sides of this equation, you get this differential equation. So the unit step function is basically the derivative of this signal. You can verify that the derivative in the negative side is always 0. And then the derivative in the positive side, in this part, is always 1, constant 1. Right? That corresponds to the unit step function. Okay. And then once we have the previous special signals, we can generate more complex signals using those special signals. For example, if we want to generate this pulsed Doppler waveform, now this is a periodic signal, and what it does is that periodically we will have a cosine omega t, a cosine signal that lasts for tau seconds. And after that, the signal will disappear for a period, a constant period. And then the cosine signal will appear again for another tau seconds. So this signal is kind of like, it's kind of Windows signal. So for every period of time, we will place a window on top of this cosine signal to stretch out part of the signal. So intuitively, we can first consider a cosine omega t. And to generate this pulsed Doppler waveform, we just need to multiply this signal by a periodic window signal. Right? And this window length is tau seconds. Multiplying these two, you will end up with this pulsed Doppler waveform. So this cosine omega t is a very standard cosine signal. We know how to generate that. And for this window periodic window signal, we can refer to this unit rectangle signal. Okay, we first generate this rectangle signal, which is centered at 0. And then we need to do two operations. We need to shift and rescale this rectangle signal, so that on one hand, each rectangle will only last for tau seconds. On the other hand, we will need to place these scaled rectangles at different locations to generate this periodic window signal. So how do we do that mathematically? So first of all, I will need to, so we have this rectangle signal, okay, which lasts for 1 second. Okay, it lasts for 1 second, centered at 0. So the first step what I can do is to rescale this so that it will last for tau seconds. And to do that, I need to change 1 to tau. So the scaling factor is tau. So basically, I need to divide t by tau. With that, we have this rectangle signal between tau over 2 to negative tau over 2 to tau over 2. Right? Because I scale the time axis by the coefficient of 1 over tau. So the time scaling factor is the reversal of this factor. It's basically tau. So then basically the length, the duration of this rectangle signal will be scaled by tau. So now the duration is between negative tau over 2 to tau over 2. Okay, so now I have a rectangle signal which lasts for tau seconds. And then I need to place this rectangle window into different locations. So let's say the locations that we want to place is, let's say here is 0. I suppose this is 0. This is, let's give it the number t. Okay, and this is negative t. And we have more window signals. So it's a t. We have 2 times t, 3 times t, and endlessly. Okay, so to generate that, this part is basically this signal, right? Centered at 0 duration tau. So the first copy of the window centered at 0 is basically rectangle t over tau. And then I need to generate this copy, which is this centered window shift to the right by t units. So that is, I'm shifting this signal to the right by t units. So I will replace t by t minus capital T. So that gives me the first copy. And then I can keep going. So that will be the second copy on the right. So we can, this is endlessly. Okay. And then on the left, we have this copy, which is shifting to the left by t units. Okay. So I'm shifting the rectangle to the left by t units. So it's t plus capital T over tau. And that's only the first copy. We have second copy, and so on. Okay. So this is the mathematical expression corresponding to this periodic window signal. And you can see we just leverage this unit rectangle signal. We do a proper time scaling and then do a proper time shifting to place them in the right locations. Okay. And so I would like you to be able to, starting from this picture, you should be able to write down the mathematical formulas, rigorous mathematical formulas that describes this signal. Okay. But this helps you understand the time shifting, time scaling, and in a mathematical way. Yeah, but on the other hand, later in the later lectures, we will see this type of signals very often, especially when we deal with the sampling lecture. So once you see this, the signals is described in this complicated form, don't be scared. It is basically a time shifting and copy and paste the signals at different locations. Okay, so you should have this picture in mind once you see this again.
I have a question.
Yes.
Can you explain the last part again where it's t minus 2t?
Oh, yeah, this one corresponds to, imagine this signal, this periodic window goes forever, right? So you have another window here.
Oh, I see. You're describing the second one. Okay.
Yeah, the second one to the right. Yeah, the second one to the right. Okay. Oh, my screen's freeze. Computer is not responding. I hope I still have the note. Let me just, in case I lose it. Okay. Yeah, 2t. So every of this rectangle corresponds to, right? It is very easy to understand. If you look at this one, it's the basic rectangle signal. I mean, we can directly tell how this rectangle signal is generated from the basic rectangle signal. Okay, so taking a rectangle t signal, rectangle t, doing a time scale in tau. So we scale the time axis by tau, by the factor tau, and then shifting this rectangle to the right by 2 capital T units. Right? And this one is scaling and shift to the right by 1 capital T units. So you can, then the picture appears. It's a periodic rectangle signal. So this is this part. And the last function, which is related to most of the homework problems in the homework 2, is the impulse function. And this is also probably the most important function that we need in this course. So let's look at this impulse function. The impulse function, or sometimes we call it delta function, is an idealized signal that satisfies the following definitions. It is very large near the original point. In fact, we will see at t equal to 0, the signal has infinite amplitude. And it is very small away from the original point. And the signal, the integration of the signal over the entire time domain is equal to 1. So these two pictures provides an illustration of how this signal is generated. We can first define this rectangle signal. Well, the duration is epsilon, and the amplitude of this rectangle signal is 1 over epsilon. And now imagine you push this epsilon to the limit 0. Let this epsilon goes to 0. And this rectangle will become narrower and narrower, and at the same time become higher and higher. So in the end, it becomes a impulse function. Okay. Or you can also define another triangular signal that has duration 2 epsilon, and the peak, the amplitude at peak is 1 over epsilon. Now these two, you can define this signal in either of these two ways. The common part is that for both of these signals, their integration is always 1. For example, if you look at this rectangle signal, no matter what epsilon you take, the area of this rectangle is always 1. Right? And also the area of this triangle is always 1. So this impulse function is really defined in this limiting sense. So you can imagine there's a rectangle or triangular signal defined in this way, and then you push the epsilon to the limit 0. You push it to the limit. In the end, they will converge to a single arrow. Okay, so this is defined as the delta function, the impulse function. Now, more rigorously, here's all the properties that we need to define this impulse function. So this impulse function is 0 everywhere except for the original point. You can see from this figure. But this impulse only exists at the original point, so it is 0 everywhere else. And then the integration, and then we can see that at the 0 point, we have an impulse. So therefore, the signal can only exist at this single point. However, you can see from these two pictures that as we push the epsilon to the limit 0, the amplitude of this signal at 0 will go to infinity. But the infinity is never well defined. Infinity is not a number. So the only way that we can define this at 0 is by defining the integration of this function around 0 gives us 1. Right? We can so everywhere else the signal has 0 value, but at this 0 point we cannot define it because, for example, if you define it as positive infinity, then it doesn't make any sense. Positive infinity is not well defined in general. So the way we define this is by looking at the integration of the signal around the 0 point is 1. And this is the same as integrating over the entire time domain, because everywhere else the signal is 0. So we can only care about this integration around this 0 point. Yeah. So then this matches the these two pictures that we have here. The integration as epsilon goes to 0, right? Integration around this 0 point always give you the constant 1. So that is the picture here. So basically, this signal is not explicitly defined as 0. We cannot explicitly define it. However, we can still leverage this property to do all the basic signal processing calculations. And we will see this later. we don't have to know the value of this delta function as 0, because there's no value there. So this is the key property that we will utilize to deal with this idealized impulse signal. And based on this property of the impulse signal, it has many nice properties that we can leverage in the calculations. And for example, multiplication, we can consider multiplying any function, any signal ft by the impulse signal delta t. And it can be simplified as a constant f evaluated as 0 multiplied by the delta t. So the signal on the left actually equals to the signal on the right. Basically, when you consider a multiplication of any function ft by the impulse function, you only need to care about the value of this signal as 0, because we know that everywhere else, this delta t takes 0 value. So if t is not equal to 0, if t is not equal to 0, we know that but if t is not equal to 0, by definition, we know this delta function, delta signal is always 0. So this equation always holds. However, if t equals to 0, the left-hand side becomes f0 delta 0. And also the right-hand side also becomes f0 delta 0. So this shows that these two are equivalent because of this multiplication of the delta, the impulse. So this gives us a way to simplify the formulas. Whenever you see any signal multiplied by the impulse signal, you can always ignore the signal and only treat it as a constant value, a fixed value evaluated as 0. So the difference between the two is that if you want to integrate the left-hand side, you have to integrate over f, because there's a variable t there. But if you want to, instead, if you do integration with the right-hand side, you no longer have any time variable involved in the signal f. Okay. Then you can treat this as a constant and only take integration with regard to delta t. Okay, so, and this property can be further generalized to a time-shifted version of the impulse signal. So if ft is multiplied by the shifted impulse, it's delta t shift to the right by capital T units. And following the same argument, we can only look at we can replace ft by f evaluated at this constant offset capital T. And the proofs is also follow the same logic. So if t now, because the impulse is shifted, so when we discuss this impulse function, we need to care about look at t minus capital T. If the entire input variable of this delta function is non-zero, then we know that this impulse is 0. Therefore, if this t small t is not equal to capital T, then this delta is always 0. So this equation always holds. Now, if this t equals to capital T, the left-hand side is f capital T delta 0, right? And the right-hand side is f capital T delta 0. So again, they are equivalent. So this shows that when we multiply any function by a shifted version of the impulse, we can replace this function by its value evaluated at this time shift capital T. So these are very useful properties in the homework. Okay? When you deal with multiplication of a signal with the delta signal. And following that, we can derive this very useful property. Now, because of this equation, we can take integration over t. Okay, we take integration over t. And with this equation, we know that this function equals to, we can replace ft by f capital T. Right? And the nice thing is that from the first line, you cannot do any calculations because the integration variable t is involved in both the function f and the function delta. And you don't know function f, so you cannot do any calculations. But once you leverage the special property of delta and then simplify this product into this one, now this f is a constant because here we only have f evaluated at a fixed time capital T. So now this becomes a constant. So we can pull this out. And then we can evaluate this integration explicitly because this is just the integration of the delta function. And for by the definition of delta function, we know that the integration equals to 1 over the entire time interval. But here we are dealing with a shifted version of delta function. So we just need to do a change of variable. Okay, you do a change of variable. Here we can do this for free and define this as t prime. Because the original range for t is from negative infinity to positive infinity. So after change of variable, the range for t prime is still the entire range. Okay, after change of variable, we still have this entire range. And then you can leverage the definition of this impulse function, which tells that this integration of this impulse always gives us 1. So this gives us ft. So that proves this equation. So that proves this equation. And if you look at this equation, it may look complicated, but looking at the right-hand side of the equation, it's the value of a signal evaluated at a specific time. So this is how we sample a continuous time signal mathematically. Okay. if we want to sample a signal f at a specific time capital T, we just do this. We just evaluate the integration of the entire signal multiplied by the impulse signal. And later on, we will see this is actually defined as a very basic operation called convolution. It looks, so at first glance, it may look quite meaningless because looking at the right-hand side is pretty simple. We are looking at a function at a specific time, but then the left-hand side gives a very complicated formula. But actually, the left-hand side gives us a system view of this signal, how the signal interacts with the system with this delta impulse. Okay. But in the later lectures, we will leverage this equation to do sampling. But here, all the equations that we show here are rigorously proved based on these two basic properties of the delta function. Okay, so this is everything we need to deal with this impulse function. And in the homework, you will need to utilize all these properties to evaluate the, well, I guess the integrations or multiplications. Okay, so are there any questions? Okay, and we have this some further properties about this impulse function. We have a scaling property. Okay, we can scale the impulse by a constant alpha. And again, because the impulse is not explicitly defined, so the way we deal with this scaled impulse function is also by considering its integration. So for this function, integrating this signal over the entire time domain gives us the constant alpha. Because this alpha is a constant, we can pull it out. So integration of delta t dt is 1 by definition of the impulse. And following this, we can also consider this time scaled version of delta, so delta alpha t. So we are scaling this time variable by the factor, by the coefficient alpha. And it turns out that it equals to 1 over the absolute value of alpha multiplied by delta t. So in this special case, we can see that a time scaled impulse function is actually equal to a amplitude scaled impulse function. So this is a very interesting property. Normally, we know that time scaling and amplitude scaling are completely different. But let's see if we can prove this. It's just by considering this integration. And we can do a change of variable because of alpha t. So yeah, that's why we get this 1 over alpha as the coefficient. So after change of variable, we get this
And this is 1 based on the definition of delta. Okay, so you see that integrating the left-hand side gives you 1 over alpha. Here I didn't discuss the sign of alpha. But this is equivalent. Therefore, we can just redefine this signal as 1 over alpha times delta t. Yeah, and this integration basically says that when we deal with the integration of delta t, we only need to consider the interval around the original point. So if we are integrating delta t between a negative, so let a be a negative number. If the integration is between a and 0 to the left, to the negative part, this means the integration never touches the original point. So by definition of delta t, it is always 0. Okay? Because this interval never touches the original point. So delta t is always 0 in this interval. And similarly, if the integration is over 0 to the right to another positive number, again, this integration never touches the original point. So this is also 0. So the only 2 cases that will give you a non-zero value is when this integration is between a negative number a to 0 to the positive side, or between 0 to the negative side to a strictly positive number. So both intervals will strictly contain the original point, where all the energy of this impulse is. So by taking the integration over these 2 intervals, we can get a constant value 1. So think about this, if a is a strictly negative number, integrating between a and 0 to the positive. So we can illustrate it, have a figure to illustrate this. This is 0. And 0 positive is to the right? And the impulse, the delta signal, is right on the original point. So because the delta signal is 0 everywhere else, so integrating, so there's nothing between a and the 0 negative. So this is actually equal to the integration that starts from 0 negative. Okay, because there's nothing between a and 0 negative for the delta signal. And then 0 negative to 0 positive, it contains the original point. So this gives you 1. This gives you 1. And another nice property is that the unit step function, which is the basic unit for constructing more complicated functions. The unit step function can be related to the impulse signal in this way. Ut is basically integrating the impulse from negative infinity to the time t. And this is very easy to understand. So you start from negative infinity and you are integrating this impulse function. You are integrating over negative infinity to a time t. Now, if this t is negative, then there's nothing here. for the impulse function. So you always get a zero integration. Once this t across this original point, you immediately, this integration immediately includes this entire impulse. And then integration of an impulse, by definition of the impulse function, gives us 1, the constant value 1. And then if t keeps increasing to the positive side, again, the entire integration will only contain this single impulse. So the integration is always 1 when t is positive. So that's why after integrating, it is like a unit step function. So there's the only jump occurs when the t crosses from the negative side to the positive side. And then the integration of the impulse will gives us this constant jump. After that, the signal vanishes in the positive domain. So the integration will remain unchanged. So this is a very nice property that mathematically defines the unit step function in terms of the impulse function. And because it is defined in the integration form, we can take derivative on both sides, and we can obtain another equation that expresses the impulse function in terms of the derivative of the unit step function. And this is also intuitive because if you look at the derivative of ut, when t is negative, we got a constant flat curve. So the derivative gives us 0. And when t is positive, we also have a 0 derivative. So the only thing that gives us a non-zero derivative is when we come at the original point. So there's this instant jump. And we know that for this instant jump, the derivative should be infinity. Otherwise, you cannot. You cannot have this continuity jump here. So that's why by taking the derivative at this point, you get an impulse. It has an infinite amplitude, but the integration is 1. Okay, so this is a very nice relation between the impulse and unit step functions. And the impulse signal can be used to model many phenomena in practice. If we consider this rapid charging of a capacitor, we have this power source connected to a capacitor, and at time t equal to 0, we will keep this switch on, and then the power will charge this capacitor. And these two figures illustrates the voltage and current of this capacitor. So once the switch is on, the voltage of the capacitor will, in a very short period of time, it will reach the maximum voltage. It will reach the voltage of the power source. And this usually occurs within milliseconds. And if you think of this as a approximation of the unit step function, right? Because this charging duration could be very, very short. So this can be approximately regarded as instant jump. And therefore the voltage signal looks like a unit step signal. And on the other hand, for the current signal, within that short duration of time, the current will go through the capacitor so that it can be charged. And once it reaches the maximum voltage, there's no current coming through it. So the signal of the current looks like a very short impulse. Okay, this current only exists within a short duration of time, and then it decreases, vanishes to zero. So the current signal can be modeled as an impulse signal. Well, the integration of the current is basically the total amount of charge that we put on this capacitor. And in fact, these two, the voltage and the current, is related to this differential equation, right? So the current is the derivative of the voltage of this capacitor. I believe, if I remember correctly, the current is, I'm not sure if this is correct. It should be the derivative of the voltage multiplied by the capacity of the capacitor. Okay. And therefore, if we model the voltage as a unit step signal, then the current is a scaled impulse signal. This is a very good example that connects these two special signals. Yeah, I think that's so that's all for this special signals. So in the homework, you will need to utilize you can see it's everywhere is all about the unit step functions and the impulse functions. And they are time shifted and time scale versions. So you can take a look at this. I think you are good to finish the entire homework too. So you can start to work on that. And if you have any questions, we can discuss them in the office hours. Okay, so I will stop here today, and I will upload the lecture video to the YouTube channel.
Thank you. Thank you.
Yeah, I will see you
you.
on Thursday. See you then. Bye-bye.